Welcome back. We're going to talk about something called potential energy in this video, and this is related to the work energy methods that we talked about in the last few videos. We had some examples. We're just going to kind of look at it in a different way. So we're going to have gravity and springs. Those are going to have what's called potential energy. And when we say potential energy, this is going to be an energy that's going to come from the position of the particle. Okay, and you'll see why when we go through and derive our equations. Now, the benefit of potential energy is we can get our work without knowing the particle's path. So if y'all remember in the last couple of examples, you had to know the exact direction your particle was traveling in to know if you were doing work. All right, so with this method, you just need the endpoints. You need to know where you're starting and where you're ending. That's all we need to figure out the work being done. All right, so that's the benefit of potential energy. So this method here is, I think, easier than the last one we just did. All right, so let's go ahead and we'll get started. First of all, let's draw a 3D system here. All right, so I'm going to define that as Z. Let's make this X. This can be Y. Okay, so now we're going to have a point 1 and we're going to have a point 2. And we've got a mass. All right, so this mass, it's got a weight. So that's mg. And basically we're going from point 1 to point 2. All right. So now we've got that. So this is basically what we're looking at. We were at a certain altitude. We're going to a new altitude here. All right, now technically I could take multiple paths to get between 1 and 2. I could go this way, or I could go this way, or I could go this way. It's not going to matter. Any of these three, we don't care. All we care about is the starting point and then the end point when we use potential energy. Okay? So let's go ahead and we'll derive our equations, and then you'll see why that is. All right, so our symbol now is going to be V. So this is a capital V. So V is potential energy. All right, so it's not velocity here. That's potential energy. And we're going to say it's equal to negative F. Notice that's a vector dotted with dr. All right, so if you think back to work, the work equation was similar to this, right? If you remember, the work equation was du equals F dotted with dr. So it's pretty similar, but now we're adding this negative sign here. That's really the only difference. And we're changing this to V. Now, let's go ahead and I want to get an equation for this dr. Okay, so r is going to be like a position vector. Okay, so let's go ahead and derive that. And we're going to do that by looking at the velocity vector. So this is now the velocity vector. This was potential energy. All right, so the velocity vector is going to be dr dt. Now I'm going to solve this for dr. So dr is going to equal the velocity vector times dt. Well, I can rewrite this velocity vector as dx dti plus dy dtj plus dz dt k. And then multiply that by dt. Now if you look, all three of these terms have dt in the denominator. We're multiplying by dt, so all of those are going to go away. So this means that dr is dxi plus dyj plus dzk. All right, so notice these are going to be basically the change in x, change in y, change in z. Okay, so first things first, we're going to look at gravity. All right, because we drew weight on here. So let's look at gravity. All right, so for gravity, our force is going to be negative mgj. All right, using this coordinate system here. Okay, it's always going to be pointing downward. So now I'm going to take this and I'm going to plug it into this equation. So we'll have negative F dotted with dr. Well, that's going to be negative times negative mg j dotted with dr, which is right here. So let's write that down. Now we've got that. Now remember, this is dot product. So the only thing you have to worry about multiplying is the one with the like unit vector. So we're going to do the negative mg times the dy. All right, the others go away because j dotted with I is 0, j dotted with k is 0. J dotted with j is I, or is 1 because those are parallel. So now when we multiply all that together, notice we've got two negative signs here. We're going to have mg dy. Okay, so that means dV, where V here is potential energy, is mg times dy. So now if you notice, we've got a differential over here and one here. So let's integrate both sides. So if we do that, we'll have V, which is potential energy, is going to be mg dy. Our limits of integration need to deal with the y value. So let's go from y1 to y2. And remember, these are altitudes. So our starting one and then our initial one, and our final one, sorry. And now, once we integrate this, we're going to have mg times y2 minus y1. And we're going to call this Vg. So this is the potential energy due to gravity. Now, if you look, our potential energy due to gravity is only dependent upon the change in the elevation, right? Or the altitude. So let's write a note about that. So the work done by gravity only depends on the change in position. All right, so we don't care how we got between these 2 points. We could care less how we got between there. We just care about the starting point and then the end point. That's all we need to know to find this term here. All right. Now, typically you don't have this written in terms of y. Usually we have it in terms of h. So let's switch that up. So we'll let y2 equal h2, and then y1 will be h1. And by making these substitutions, this equation will work regardless of your coordinate system. Okay. So now with that, we can say that Vg is mg times h2 minus h1. And you can also write that as delta Vg equals mg times delta h. Okay, so there you have it. So this is your potential energy due to gravity. And now let's go ahead and look at the sign notation. So if h2 is greater than h1, let's look at what we'll get for our sign. If this one's bigger than this, we're going to get a positive number. All right, so our delta Vg will be some positive mg delta h. So here our height increases, and we're working against gravity. All right, so we're going to have a positive potential energy. So the way I always think about it, I'm not sure if it's 100% correct, but this is the way I think about it. If we're increasing our altitude, I'm getting more height. I have more potential to do energy, right, because I'm higher up. Now, if the opposite happens, and if h1 is greater than h2, well, now delta Vg is going to be negative mg times delta h. And in this case, the height decreases. So now we're closer to the ground, So now we have work done by gravity. All right, so work's helping you, or gravity's helping you out in this case, right? So here you're going against gravity, here you were having gravity help out. All right, so there you go. And you don't really have to memorize these because you'll know your final and starting points. So you'll be able to figure out if it's positive or negative just by plugging in the values you have. Okay, so that's what we have for gravity. So just remember it's mg times the change in h. Now let's talk about springs, because springs have elastic potential energy. So think about a spring. If you have a spring and it's like this, and you push it to the left and compress it, you know it's got energy there, right? Ready to be released. Okay, because if you let it go, it's going to move back to the right. All right, so we've got elastic potential energy in here. And again, it's caused by a position, right? Because you're changing the position of the spring. So let's derive our equation for this one. We're still going to start off with the dV, remember V is potential energy, equals negative F dotted with dr. And for this one, let's go ahead and use this same diagram here. If we have a spring force, we got F equals Kx. Okay? So Kx is our spring force, and it's going in the direction that's opposite of my positive x. Okay, so with that, I'm going to have dV equals negative times negative Kx and then dx. All right, so we don't need a dy and a dz because all of the motion is in this x direction. All right. And again, and this is negative because the force, we're drawing it that way, positive x is this way. Now this one we're going to call VE. So E stands for elastic. So if you see that, you know you're dealing with springs here. And if we want to get that, notice there's a differential here and here, so we're going to integrate both sides. So this left side gives us the VE, and over here we're going to have the integral from x1 to x2 of kx dx. Once you integrate, get that your elastic potential energy is kx squared over 2. You're going to evaluate at your starting x and then your final x. Now remember, this x here is the amount of stretch or compression in the spring. It's not the length of the spring. Okay, so a lot of students want to put in there that it's the length of the spring. It is not. It's the stretch or compression amount. So now if we plug this in, we're going to get delta VE equals 1/2 K times x2 squared minus x1 squared. All right, so that is your term for the elastic potential energy. So you'll use this anytime you have a spring in your problem. And then again, you can check out the sign notation just by looking at this right here. So if your spring deformation increases, then that change in potential energy is going to be positive. So I like to think of that as having, more potential to do energy, because if you compress this spring all the way over here to the left, let it go, it's going to have more energy than if you just compress it a little bit. Okay. And then if the spring deformation decreases, well, then you have the opposite case. So now delta VE is negative. All right. And last little section we got right here, the work-energy relationship. Now we're going to go back to U So remember, U is the work done by all external forces except, this is key here, except gravity and springs. All right, so any other external forces that are applied to your particle is going to be taken into account here in U. All right, and we can say that U equals delta T. Remember what T is. T is that kinetic energy. So that is the 1/2 mv squared. All right, and then we're going to have plus delta Vg and then plus delta Ve. Okay, so this is going to be the equation you're going to use. All right, now a lot of the times this term over here is going to be 0 because you're not going to have an external force, but if you do, it's going to be the force times the displacement in the direction of the force, just like we did in that last section. All right, so now we've got that. Okay, and again, notice this is delta T, so actually let's just write it out. So delta T will be the 1/2 mv, you'll have V2 squared minus V1 squared. All right. So there we go, and let's see, what else? We could also say one more thing before I forget. We can write that this equation is also equal to delta E, where that capital E equals the mechanical energy. All right. So now we've got that. And if E is constant, then that means that we get our law of conservation of dynamical energy. Okay, and that's because, you know, delta E here would go to 0. All right, so that's it for that. The main thing you need to know is this right here. All right, so just know we've got work, and it's going to equal these 3 terms right here. Okay, so now we'll stop here because this is already almost 18 minutes. We'll stop this video, and then we'll pick it up next time with one of the examples.